So what I've got set up here today, I'm going to take care to keep my fingers away from the live bits, is a variable speed drive which I'm running into some inductors. So these two inductors are connected together in the middle, and the middle phase, the V phase, is connected to the connection. The red phase, the U phase, is connected to there, and the blue phase, the W phase, is connected to the second inductor. I'm looking at the current through one of the phases, and I also have my scope connected across the output of the drive so that you can see the PWM. So what I've set this drive up to do is, and I'm going to the menus, I'm going to menu 5, the rated frequency, so that's 100 Hertz. So at full voltage it's going to be producing 100 Hertz, or at 100 Hertz it's going to be producing full voltage. The motor rated voltage I've got set to 5 volts. In other words, at 100 Hertz we're going to be producing 5 volts across the output. These are 1 millihenry inductors. So at 5 volts we're going to have full current through the inductors which the drive is rated at. We're also going to go over 100 Hertz and see how that affects the current, because the current is dependent on the reactance of the inductors and the resultant impedance, which is a consequence of inductance and your copper resistance. So I'm going to go back to the current menu. Menu 5 is your motor setup, menu 4 is your current setup, and parameter 1 is current feedback. So that's currently on 0, so this little indicator over here is not lit. So when I close this switch over here, that indicator is lit and we can see some current flowing. My tongue tester is showing some current flowing, and we can see some PWM happening on the output. As a matter of interest, let's just go see what I last had that set to. So I think we had it jacked up fairly high, as I recall. Let's have a look. No, it's 3 kilohertz. Okay, that'll do. Go back there on current. So now changing this to hertz, we can see the frequency over there, like so, coming up, and we can see our current on the tongue tester coming up. The PWM is not much to look at this in this experiment, but I put the scope there and we can see things happening. So I'm going to 100 Hertz, and what has happened is the cooling fan in the drive has come on, because if we now look at the current, we're at full current on the drive. So this is basically a full load test at the output of the drive. Now if I were to carefully separate the supply leads so that we can put the tongue tester on there. That's a supply lead. That's a supply current to the drive, 400 milliamps. Now why is that less than the output current? That is because the current being drawn on the supply is the power being delivered on the output side, because we're not at 230 volts on this secondary side, the output side, but at a much lower voltage. So it is 5 times that current. This is probably battling to measure it, times the square root of 3. So it's 5 times 4 is 20 times the square root of 3, which is 1.7. So 5 times 4 times 20 times square root of 3, call it about 35. So dividing that into 220, going to be about 20%. Now look, there's also losses involved here and so on. And also this is not a perfectly accurate instrument. So yeah, it comes to about 400 milliamps on the supply that we're drawing to produce 4 amps on the output. So that's how power conversion works. What is coming out is V times I. What's going in is a fixed voltage and only the current changes. Okay. And over there you can see the PWM. And if I speed this up to quite fast, where's my hold button? There one can see the switching happening and then the decay afterwards. And that's what that looks like. It's fairly fast, that's 20 microseconds. So that's happening 1, 2, 3 within 60 microseconds. So if we go back to 2 milliseconds, which is current where you generally look at mains waveforms, that is what you see. So we're at 100 Hertz, so that's 2 milliseconds per division. So we're at roughly 2 milliseconds between waveforms, or just over. And generally we're at double the frequency, so that would be 100 Hertz. Let's see. It's battling a bit to measure that. I've set it to 20 milliseconds. Yeah, it's kind of battling to measure that. The duty cycle is very short because we've only got 5 volts coming out of here. So those pulses are very short. So that's what the output looks like. Now the current waveform, if you were to look at it, is a sine wave. And that's what the motor is concerned with when you're driving a motor, because the current is what produces the magnetic field. And let's turn that back down. As the thermostatically controlled heating fan is running to cool the IGBTs inside here, and it's automatic. It doesn't turn on the fan unnecessarily. That stops it putting hours on the fan and stops it sucking dust into the fan and into the drive unnecessarily, because the airflow goes through the drive. It's got to cool the capacitors and the IGBTs and the input rectifier and so on, the rest of the electronics. Now let's do something else. Let's go back to Hertz, and I'm going to take it all the way to 150, 200 Hertz. You can see that the current went up. Let's go back into current. But now it's come down again. So let's go down again to 4 amps. Go back to 100 Hertz. Go back into current, we're at 4 amps. Let's go back to Hertz. Let's go back to 200. Let's go back into the current. See how that has come down again? That's because the reactance, the impedance of the inductors has gone up because of the frequency. In other words, the reflected load, the reflected resistance has increased, so the current went down. So that's why you're sitting at 1.6 amps now, or 2 amps on the VSD. So that once again illustrates what I was doing yesterday with induction motor, where I was running it super synchronous. Because of the reactance, the impedance goes up and your current starts to come down again. If one were to keep on going, that would keep on decreasing some more, but 200 Hertz demonstrates what we want to over here. So we know that we've got good load capability on this VSD. On very big VSDs, that's particularly useful because we don't have hundreds of amps available of the mains for testing, and we don't have the ability to absorb hundreds of amps of power on the motor side either. So a dummy load like this is what we use to make sure that the electronics on the output of the thing is doing what it should, and there isn't a problem, and that our current feedback on our drive is also reporting correctly. That's very important, and also that the IGBTs are switching correctly and so on. And the other thing is you want to check that you're not getting any DC coming out. In other words, you're getting asymmetrical AC waveforms. So now putting the tongue test on there, I should see no DC current, which I don't. I've got it on DC over here. Okay, that's the other thing that we look for, is that there's no DC coming out of the drive. In other words, one side of a bridge is partially switching or something like that, or not switching at all. You don't want to get DC into the motor. There's various problems that arise because of that. The motor doesn't run very well. It draws a terrible amount of current and it runs hot. None of it's good. So we check for DC as well. So that's basically what's going on here. You can do it with 3 inductors, where you run each phase through an inductor and then store the other side out. But it's sufficient to also do it just at 2 inductors like I've done here. So if I go to the middle phase like this, and I look at the current, it's actually reporting slightly higher. Let's go back. There we go. So there is a little imbalance on the current when you're running it like this, but it's okay. If you've only got 2 inductors, you can still do the test. It works alright. Let's see what the current in this piece of wire over here is. Gonna gingerly grab it, and there's your current. It matches up with that. Very good. So this is interesting stuff. This is electronics. This is power electronics. We're working with inductors. We're working with switch mode stuff. Working with variable speed drives. And we're learning about drives. And drives are not hard to work with. I've got my potentiometer here for a reference. It's a 0 to 10 volt signal, and 1 is 0 volts, and 2 is your reference, and 4 is a 10 volt supply from the drive. Okay, simple as that. Here we have a simple contact closure between pin 9 and pin 12 on the variable speed drive, and gives it a run. You tell it that you want to work off the analog input, and it then assumes that you're going to be running it off a terminal start. If I stop it, well, I've got to disable it to change the mode. It's not going to let me do that while it's enabled. This is a drive with customer damage. The enable input on terminal 11 is blown. So I inherited this because they replaced it. So in the software I've inverted terminal 11 so that the enable input stays high without needing an enable input or a e-stop input or disable input, whatever you want to call it, on terminal 11. On these little drives, by the way, there's all the connections over there on the label on the underside, and there's all your parameters on the front. They're really easy products to get on with. This one over here is a 0.75 kilowatt drive. It's 200 volts and the rated current is 4.2 amps. On the back I can connect a programming cable to my PC. That's RS4852 wire, and one just needs a USB to RS485 converter cable, and one can communicate with this and program it with the PC software, which you can download from the website after registering a profile. It's free software. This stuff is very user friendly, and that's the story. We've played with inductors. No heat was generated in there. These are rated at 28 amps. They're quite big inductors, so 4 amps isn't going to produce any heat in them. You could use them on a bigger drive. I happen to have them. They're a suitable impedance for the size drive, so there we go. The demonstration has been done, and that's going to conclude this little talk. I think you got to see in detail how it works when we do a load test at work. I made a short of it a while back, but it was not going into detail. This was a detailed video. So ladies and gentlemen, thank you very much for being here today. Thank you for spending the time to watch the video. Take care, and I'll see you back for more fun stuff sometime soon. Cheers.